Let's start. Welcome to this seminar organized by Wide Bandgap Power Center, and special welcome to our speaker today, Claire Troadec from YOLE Development. We will have about 1 hour today for presentation and questions, so please prepare your questions and let's be efficient there at the end. So a few words about Claire Troadec. Claire obtained her, Claire is the director of the Power and Wireless Division in YOLE Development, and her activities cover power electronics, batteries and energy management, compound semiconductors and emerging materials, RF devices and technologies. Claire Troadec obtained her Master of Science in Applied Physics with specialization in microelectronics from INSA in France. Then she joined NXP Semiconductors and worked for 7 years with the CMOS technology as process integration engineer at IMEC R&D facility. She has co-authored and co-authored 7 US patents and a number of international publications in the field of semiconductors, and managed her own distribution company before joining YOLE Development in 2013. So, Claire, I would say the floor, no, I say the screen is yours.
Screen is mine, yeah.
Yes.
Okay, thank you. Thank you very much, Mitek, for the introduction. It's a pleasure to be here online. So we're not face-to-face yet, but definitely we hope it will come next year. So I'm gonna indeed cover the very interesting markets of compound semiconductor. So we'll focus today on power GaN and power SiC. All right, so let's start. Okay, just a few words about YOLE before we go in the technical topic. The way we are organized, so we are a market research company covering the semiconductor area. So we have 3 main divisions in the company. So I'm heading the Power and Wireless division, as Mitek explained. I think the core of the activities of YOLE were historically in MEMS, so photonics and sensing. The company has been created in 1998, and we moved from electrons to photons. So now we cover also lighting, photonics, imaging, display also with LED, micro LED, mini LED, and things like that. And then we have a last division covering more the mainstream semiconductors with memories, computing, packaging and advanced packaging, and manufacturing, making the link with equipment, material, foundries, fabs, and so on. So this is how we are organized to cover the full semiconductor market research. Okay. So let's go now in the topic. I'll also look at the timing to be sure I'll respect the timing. So power electronics. I just wanted to give few words. I know you're pretty familiar with that, but just to explain the dynamic, the trends that we are seeing in power electronics before going into the compound specific drivers. So as you know, we moved from mechanic or thermal kind of energy, well, let's say management, to more electric functions. So electrification, batterification is a big trend, meaning battery-powered cordless end systems. We are requiring more autonomy in the systems. We are requiring more smart solutions, so using the energy more efficiently. We are requiring more flexible, modulable system to adapt to the different requirements for the system integrators. We are requiring, of course, green manufacturing, automation. So this will become more and more strong, of course, with the clean energy. So really this CO2 reduction emission, looking at the impact also of the manufacturing activities when it comes to using energy. So all this goes in the right direction. So those are the drivers. So which means the power electronic devices, systems and applications are getting stronger, greener, smarter, and more connected and integrated. Okay, so historically, for power electronics, the market really started for industrial applications in the 1970s, with, of course, all the different fabs to manufacture goods, requiring power conversion for motor drives or such applications. It's growing again, the trends for this fabrication motor drives, where now we need electrification, more electrification of systems, and automatization with the manufacturing 4.0 and so on. Then we got the second growth relay with consumer and computing, with smartphone, laptops, or all the consumer goods, of course, using power conversion systems, so more low power energies, power ICs, and things like that. And it's again a trend that is growing more now for the data centers, the 5G applications, so more high power than the consumer ones. Renewable also started as a growth relay in the 2010 with photovoltaics. So there was a boom by that time, and then it collapsed. And again, now we're seeing the high implementation in countries such as China, implementing a lot of PV farms and a lot of incentive mechanisms that are reboosting these renewables. So which means photovoltaics, but also windmills, windmills being also very important, being deployed offshore, onshore. And automotive. So now we are talking a lot about automotive, electric vehicle. As you've seen, there's a strong revolution, and COVID amplified more or less this revolution. Governments pushing for strong CO2 regulations. So automotive is the next, is the growth relay now of the power semiconductors. And I will show you how it's transforming the overall supply chain, the demands, and so on. All right, so if we summarize power electronic systems, as you know, it's a very fragmented market. So we have low power applications for consumer goods, power supplies, white goods, so where we require more compactness in integration and low cost solutions. Then we have the medium range applications, that's motor drives, so huge markets for power electronics, uninterrupted power supply, the DC charging station for electric vehicle, which is starting to be deployed very massively, electric vehicle. So those require more integration, more reliable also functions, and to deal with thermal management as we are approaching higher power levels, okay? So getting power in is never a problem. The problem is to get the power out, the heat dissipation, this thermal dissipation with the losses with the power conversion. And then we have the high energy applications, the high power applications such as rail, grid, wind, some of the medical applications with IRM and things like that. So then we need very highly reliable systems, good thermal management. So packaging will be key for sure. And there, of course, you will have more costly solutions because we're dealing with safety, we're dealing with possibility of explosion. So packaging will be key in these medium to high applications. So I just wanted to show you that really power electronics is a highly fragmented market with very different demands in terms of power levels, end user application, and integration level. And this will be reflected in the technology choices supplied by the players in the packaging solutions also. Okay, so if we summarize the solutions we have today for power electronics, and we take a very simple plot where we look at the operating frequencies versus the switching power. So of course we have some thyristors, for example, devices that are more suited for the high power capabilities, lower operating frequencies. So applications such as grid, wind, rail, where we have high power demands, will take some devices such as IGBT or intelligent power modules for some of the like, or IGTC. So really these high power devices that can conduct high current with the safety requirements. Then we'll have on the lower power side, so for the consumer goods, some of the power supply, the white goods, we will see MOSFET transistors. So having the benefits operating of higher frequencies. So to summarize, we have MOSFETs, low power, high frequency, and our IGBT, high power capabilities to deliver most of the power electronics applications. And then we have compound semiconductors making their entry, so silicon carbide MOSFETs and gallium nitride HEMT. So to simplify, we'd say silicon carbide is more suited for the high power applications, while gallium nitride would be more suited for the high operating frequencies applications and low power solutions. And then we would find a competition zone between silicon carbide, gallium nitride around the 600 volt devices. Okay. Now, if we look at the overall market in power electronics, let's size this. So it's a market which is a little bit less than $45 billion, so a huge market. And if you look at the splits in terms of solutions being pushed by the technology providers, you will see power IC are making most of the market. So half of the market for power electronics is coming for power IC. So those little chips embedded in all our consumer goods, in smartphone, in laptops, to manage this power conversion. Then you would find discrete devices, so the MOSFET, the IGBT, and so on. And then you would find power modules. And as you're seeing, so the market is evolving, of course. It was impacted last year in 2020 by COVID, largely due to supply chain disruptions, company shutdowns, and lower production rates, especially in the traditional automotive business. But overall, this is a growing market, dynamic market, with a 5% CAGR from 2019 to 2026. And the most dynamic part of the market is the power modules, where we're seeing even 11% CAGR, so a compound annual growth rate in the same time frame. Now, if we look more specifically into the devices, the devices and the modules, and we exclude the power IC, making half of the market, again, we will find the same picture with the impact of COVID last year, the growth of the market. And within this discrete and module, we'll see the majority of the markets is driven by the MOSFETs, discrete MOSFET devices implemented in a lot of applications. We'll see a lot of rectifiers also. And for the rest, you will see a highly growing market for the IGBT modules. So more and more IGBT modules embedded for example, electric cars, and silicon carbide modules also here in yellow, strongly progressing. So this is the split we are seeing in terms of discrete devices and power modules. So if we look now in this compound, what is compound taking in terms of market share for this overall power electronics industry? And now we have a close look because we follow this market quarter by quarter since 2019. And what we are seeing today and what we envisage for the future is that today the compound share in 2021 from the overall power electronics business is small, but it's highly progressing. So today, SiC represents 4% of the market value for power electronics, and we expect it will represent 13% in our realistic scenario. In the optimistic scenario, it could be even more if the adoption in the electric vehicle for the Chinese brands, the 400 volt electric vehicle could be higher. But at least we anticipate 13% market share by 2026. And for gallium nitride, it will be around 5%. So we are both seeing silicon carbide and gallium nitride to penetrate, to take more share on the overall power electronics markets. So then reasons why is that? What are we talking about when we say power GaN, power SiC? So we'll start with power GaN, just as a reminder how the story started. So the first devices we've seen on gallium nitride for power applications were thanks to international rectifier in the year 2010. So it's kind of a young technology if we look at gallium nitride. Then, of course, we've seen the acquisition of international rectifier by Infineon. We've seen power integrations also started with the acquisition of Velox Semiconductors, also in the same 2010s years. Then we've seen GaN systems also entering these markets, securing the supply chain with TSMC. We've seen Navitas as founded in 2014 and getting more Series A and B investments of $40 million to progress and deliver the solutions. We've seen partnership with some electric vehicle players, so automotive players. I will come to that. Again, TSMC providing the manufacturing capabilities of Navitas, also securing the supply chain when it comes to packaging with OSAT players Mcore. We've seen Innoscience, also a Chinese player getting some private investments. Okay, so this is really how it started. Continuation, players such as International Rectifiers, then Infineon, Power Integration, Transform, and Navitas. And if we look more recently from the 2018, so we continue the roadmap, we are seeing a strong acceleration in terms of players entering in the GaN area, in terms of partnerships. So we will find again GaN systems having some collaboration with many players here. We highlighted ROM, getting some private investments by some automotive players, here Toyota, but also BMW as an investors. We could notice a lot of partnership in the electric vehicle automotive environment. So Mirelli with Transform. Here we're seeing Nexperia with Ricardo. We are seeing also Navitas with Brusa, Renault with ST. So automotive players on the background supporting the GaN industry and investing to get this partnership ongoing. And lately we've seen massive, so what we say a SPAC, so Navitas going public with a $1 billion valuation, so a really huge valuation. So overall, when we looked at the total investments made in this GaN area since the year 2010, it's more than 2.5 billion, which have been invested by the players. So really more dynamism coming on in this GaN power industry. Okay, so now what for? What is the holy grail of GaN power? Where can it be used? So the holy grail, how the market started, is fast charges. So charges for the consumer, for the smartphones, devices. That's the sweet spot today of gallium nitride. So as you know, the smartphones, they are getting larger. They are getting stronger computing capability, higher communication capabilities with 3G through 5G implementation. So all these technology features are more demanding on power. So it drains the battery down. So we need to charge our phone more often, and the need for fast chargers has then increased. So we are seeing, of course, silicon-based chargers. Historically, players such as Energy, Apple integrated such fast chargers. Fast chargers meaning more power delivered by the solution. So 65 watt, for example, is a solution that we are seeing quite, I would say, quite as a standard for fast charging. And then we've seen many players. So Oppo was the first player to integrate a GaN-based fast charger back in 2018, yes, with their accessory chargers. So first players integrating gallium nitride in accessory chargers, aftermarket chargers, and some players integrating gallium nitride in their inbox chargers. And there's a strong, more or less, change in terms of how will you provide the charger. Will it be inbox, meaning with the phone that you will buy, or will it be accessory charger, meaning big players we've seen like Apple, Samsung, Xiaomi, Huawei, Google, they have out-of-the-box chargers now. So what impact does it have on the gallium nitride? Does it increase the adoption to have this choice of buying a specific fast charger where you can have, thanks to the gallium nitride technology, it allows miniaturization of your system, so more power efficient. And in terms of cost perspective, as we are showing here in the plots, so miniaturized solution, here we are showing here with the cased volume, so the overall volume in cubic centimeter. And in terms of price per power, so dollar per watt, we are seeing very competing gallium nitride technologies adopted by players such as Xiaomi, Lenovo, and so on. So we're seeing more and more design wins by GaN device players such as PI, Navitas, Innoscience, ST, The design restrictions are strong for the inbox, so it does not always make sense to implement GaN, but nevertheless, this is how the market really took off in 2018, and this is what makes the strong growth of this gallium nitride market. And here are the solutions delivered by the players. So who could be next? Of course, Infineon, onsemi, to be seen what kind of solution they could suggest, they could propose for this fast charger, consumer fast charger. And lately, we've seen Apple also adopting the technology for their MacBook Pro. So this times more on the laptop and 140 watt adapter. So really high power, fast charging, miniaturized solutions. Okay, so overall, how much does it represent in terms of market value if we look at this gallium nitride? So here, this is the plot at device level. So in 2021, the market is around $100 million. We are expecting it to grow to more than $1 billion by 2026. And as you see here in gray, this is the consumer, mobile and consumer market. So it's mainly driving this gallium nitride growth, indeed, with the fast chargers, as we've seen for smartphones, also for laptop. We think that other emerging consumer applications which will come, such as LED drivers, Class D audio, e-tools, home appliance, where today they represent small market volume, but definitely they will benefit from the price erosion with the gallium nitride-based fast charger industry. We are seeing also expecting telecom and infrastructure also to adopt more these gallium nitride-based solutions. And this is mainly due, you see a jump here from 2023 to 2026. There will be strong regulations coming in Europe in 2023 to reduce the power consumption, to improve the efficiency of the systems. So this will push the gallium nitride solutions. And just an indication today for a 5G base station, they are really highly power hungry compared to the 4G base stations, and they consume like 40% more power than their 4G counterparts. So it could go to 11 kilowatts power consumptions for a 5G base station. So definitely GaN has an advantage there. Again, efficient technology that will drive the adoption for such solutions in the telecom and infrastructure. And then in orange, you will see the automotive, what we call automotive and mobility. Mobility being the low e-mobility with scooters, with e-bikes and so on, but also automotive with electric vehicle. So there has been a growing interest in gallium nitride for onboard charger, DC-DC converter applications. So we think it will start with DC-DC, then onboard charger, possibly inverters, but more after 2026. And inverters could be great more for the lower e-mobility solutions. So players there would be EPC, Transform, GaN Systems, Texas Instruments. They are AEC qualified, automotive qualified. And other major IDMs are also entering there, like ST, Infineon also looking into that. Okay, so this is the split for the gallium nitride markets. If we look very quickly on the market share, today at device level, power integration is capturing most of the market together with Navitas. Then we have EPC, historical player. And then we are seeing strongly involved players, strongly progressing players such as Innoscience, Transform, or a historical player again with GaN Systems and others. So if you look overall in the change in terms of market share, we are seeing the progression of power integration. So they have a different technology with the GaN Sapphire. So it limits the output power to a few hundreds watts, but their strength is the channels they have in place through their big company Power Integration with customers, the broad product portfolio that they can offer. So not only having the GaN solutions, but also being able to deliver gate drivers and other complementary power devices. Navitas is a very American player, is very strongly progressing. We expect around $27 to $30 million this year, 2021. So they are getting more and more design win for fast chargers with their system on chip solutions. Then we have EPC. They continue to penetrate various markets, including the datacom, telecom, more like the Transform and Infineon-like. So not so much focusing on the consumer yet, but historically, this is how they started in some of these niche markets requiring high power efficiency applications. Then we would see maybe a few words on inner science, as I said, so they are more diversified than Navitas. We expect also their GaN revenues to again grow strongly this year. Then they have LED drivers for the fast chargers, also with the Chinese OEM. They're also looking at wireless charging for e-scooters and so on. So a lot of players involved. For Infineon, it's not the priority yet, so low revenues. Their priority is more on the silicon technology and silicon carbide. And they also conduct this dual path for GaN with two teams, one focusing on E-mode from their Panasonic IP acquisition and another one on D-mode through the international rectifier heritage. ST also progressing and being able to deliver solutions both for D-mode and E-mode, and as a big power device player, definitely they will benefit from the established link with their players, their know-how in packaging, in design, and so on. And maybe a last word I could say in terms of player on semi, as they are no more in the gallium nitride race. Their focus really is on silicon and silicon carbide. They're selling their gallium nitride fab in Belgium. So they're focusing more on the drivers, silicon drivers for the gallium nitride devices. And they are well positioned there with TI on these drivers for GaN devices, because this is one of the challenge with these devices operating of high frequency, how to drive them, how to operate them. A few words on the cost. When we've discussed with Meetech, told me cost is something which is always very interesting when it comes to compound semiconductors. So here it's thanks to our sister company, System Plus Consulting. We've looked at a Navitas GaN on silicon solution, so system on chip, 650 volt. And also we make a general comparison trend from all the different GaN on silicon HEMT operating at 650 volt. And you will see the epitaxy would represent 1/3 of the cost, and the yield losses at different levels of the manufacturing, epi and so on, 40%. So epitaxy still is responsible for quite a big fraction of the overall cost. So the main technical challenges are being resolved because we're seeing the solution now in the consumer markets. Improvement are needed indeed when we'll see the transition from 6-inch to 8-inch for the GaN on silicon. So the epitaxy has progressed significantly. However, it remains the main issue. And the yield losses, when we will see the transition from 6-inch to 8-inch, will also be some kind of challenge. But the cost of GaN on silicon is going to be a key factor in penetrating the consumer market. It has the advantage of being able to be developed on an 8-inch platform that can solve the cost and capacity issues at the same time. But today, few players have launched the 8-inch platforms. Some are undergoing the R&D and transitioning from 6-inch to 8-inch. So we expect to see this 8-inch platform to become the main size for GaN on silicon in the next 3 years. That's the idea. If we would look at GaN on sapphire, so the solution from power integration, so there, as the lattice mismatch is smaller between GaN and sapphire, the AP wafer cost can be very low. So if we look at the mature LED supply chain, the cost of a 4-inch GaN on sapphire AP wafer is less than $20 at high volume. So the layer will be thinner, less complex buffer layers is also needed, so that provides a cost advantage. But this industry, it's unlikely to transition to 8-inch, 6-inch and 4-inch are still the mainstream platforms for the GaN on sapphire. Okay. So if we look at the different technology for GaN, so as we've said, we can have different substrates. So today, the GaN on silicon, a solution from Navitas, from all these American startups, is representing the main market share. Sapphire, the GaN on sapphire today, it's only PI operating these solutions. In the future, bulk GaN could come, so Japanese players are very much focusing on that. But today the cost is very high, so there's no real motivation to transition and very low wafer sizes. Technology, D-mode, E-mode, will need a split and will need the dual technologies. I think there has been long debate on which technology is the best one. It all depends on the application. So I think now the players understand it and are delivering a more complete portfolio with D-mode, E-mode. So D-mode mostly for high power applications, E-mode better leverage of the low losses. That's more or less how we would simplify the message. In terms of voltage, so 650 volt is making most of the markets. So the low power solutions are there. They are R&D to again look at more high power devices. In terms of integration, discrete is making half of the market. System on chip, so solutions such as Navitas, 1/3 of the market. So system on chip is preferred for the low power applications, the compact designs. But system in package can be very interesting when it comes to high power applications. And usually we are adding a silicon driver. So it's represented 1/3 of the market. Different packaging platforms and different topologies. So the technology choices, again, will just depend on the application. So if we look in the future, just a general roadmap for the gallium nitride power devices, as we said, it's some kind of a new technology, first device in 2010. Let's not forget it. It's not as mature as silicon carbide. It has started with the high-end applications like PV inverter, so delivering power efficiency and miniaturization of the systems, which is always very interesting. When you want to install the solution, you require less manpower, so you can benefit from a higher technology, higher cost of the technology, but when you do the implementation, you will see the benefit. It has strongly evolved with the fast chargers for smartphone. And the next growth relay, continuing in the consumer market for laptops and so on, other consumer applications. Next growth relay will be data centers, electric vehicle with onboard charger, DC-DC. In the future, industrial markets, and let's see, players are looking at inverters, but today it's more for the smaller e-mobility or smaller e-cars with lower power levels. Okay. That was the picture for the power GaN. So let's save some time for SiC, also a very interesting material. So there the picture is very different when we look at the silicon carbide. First, it's a more mature technology. I mean, first devices, diodes in the year 2000, 2003 in the market. So it has a little bit more maturity than gallium nitride. And there, the main driver for silicon carbide is automotive. You will see here in this orange color. So again, we are tracking this market on a quarterly basis. And definitely automotive, electric vehicle are driving the growth, the future growth of the silicon carbide market. You've seen, like here, if we look at the yearly picture, we've seen 2020 again with the COVID impact. It also has impacted the silicon carbide through the automotive production. Players such as Tesla and others had to close some of their fabs. So this is why in 2021, if you look at the year-over-year growth, it was quite high, 51%. Because it was the end of these lockdown measures, the supply chain disruptions that negatively impacted the markets, mostly in the first semester of 2020. Certainly, electric vehicle is now the priority of the OEMs, of the governments. You've seen in Europe, all new cars have to be emission-free by 2035. Similarly, in the USA, Biden is pushing for EV cells to make half of the US cells in 2030. So the growth will definitely continue. But apart from automotive, which will represent around 60% of the markets, let's not forget about energy, so wind and photovoltaics, and industrial applications. So industrial applications that are expected to grow in the long term. Okay, I think I can that one. If we focus on the electric vehicle, so you know there are a lot of different power systems, so you can, and different kind of electric vehicle, full battery electric vehicle, fuel cell, plug-in hybrid, mild hybrids, and thermal vehicle. So for all the electrification, you can implement onboard charger or the main inverter, the traction inverter, to really have the energy conversion from the battery to the wheels. The boost converter in some specific model like Toyota and so on, and the DC-DC converters when you want to use the energy from the high voltage battery, 400 around the 400 volt range, to the 48 volt battery. Then you would need this DC-DC converter. So you would see IGBT or MOSFETs are silicon-based solutions, and depending on the power level, you can also see gallium nitride as a nice second option, or silicon carbide as a nice second option. And basically, silicon carbide devices could replace silicon-based IGBT and MOSFETs in almost all the EV applications. But the holy grail, where the value is in the main inverter. So making the transition from the high battery voltage to the motor with this DC-AC conversion. Okay. So now if you are an OEM, the choice of implementing silicon carbide or not is very, very complex. The full mission of the OEM is to deliver a vehicle with a good performance cost trade-off. And for electric vehicle, it comes with a long driving range, okay? Because for the consumers, to solve these anxiety problems, you will deploy the DC charging station on the road. But also, of course, the driving range of the vehicle is also an important parameter. So to achieve a long driving range, either you pay a premium in the battery, so you implement a huge battery, big power, good technology, NMC, what Tesla did in USA, and now they're implementing lower cost battery solutions in China, for example, using LFP kind of technology to fulfill more or less the needs from the consumer in terms of being able to buy the vehicle or not. So you pay a premium in the battery, and then you would deal with silicon-based IGBT for the power conversion, or you would use a less high-end battery, and you would pay a premium in the power conversion by implementing silicon carbide. So both solutions are possible and will help you to come up with a longer driving range for your vehicle. What will the market look in the future? What we think is that the IGBT modules today are the preferred solution for the main inverter in electric cars. It will continue to be so, but you're seeing here in green the silicon carbide-based modules, which will strongly evolve. So like 34% CAGR we expect. So overall, what we expect is to see both routes to continue. Silicon-based solution together with silicon carbide. Silicon carbide will be more suited for the high-end BEV, the high voltage battery, 800 volt vehicles. Then it makes completely sense to implement a silicon carbide-based solution, because you would go to 1200 volt devices, meaning more mature technology, and the cost premium compared to silicon would be less, giving you more power efficiency and more added value from your technology. But both silicon-based and silicon carbide-based roads will coexist in the future. Now, when we look at the players, so who's there to support this very dynamic silicon carbide supply chain? So as you know, the big race is on delivering high quality substrates, and that's a very difficult task. So today the main player is Cree, Wolfspeed, now being able to deliver high quality crystals, high quality silicon carbide wafers. SiC Crystal also being bought by ROM, so with the internal manufacturing capabilities, internal sourcing. Norstel, as you know pretty well, being acquired by ST. Also what the device players are doing is try to secure the supply chain and being able to have a vertically integrated business model by having their own supply. But this is really not a simple exercise. We've seen lately also ON Semiconductors acquiring GTAT for their bull capacity and being able also to have their own wafers internally. Let's not forget also that to bring the solution to the market, you need to have a good packaging technology. So the power module packaging is key for the integrated device player, but today they are more selling the bare dies, like the ROM, the Cree, they are selling bare dies, and they're making partnerships with module makers, tier 1, to deliver the solution. So the power modules is also key, and players such as Danfoss, Semicron, of course, are also entering this market to use their know-how, internal know-how, how to integrate this silicon carbide-based chip, because you need to completely redesign your power module with new substrates, silicon nitride-based substrates, new interconnections, because you're dealing with high power levels, you're dealing with smaller die sizes, so higher power density. It really is a complex task. So we are seeing, again, a lot of players involved in these environments, Chinese players, OEMs also being very eager to adopt silicon carbide-based technology to really get this technology on their territory. Okay. We also make a special outlook on the Chinese players. So Tanker Blue, SiC progressing very well to deliver silicon carbide-based silicon carbide substrates, not reaching the quality levels of the American or European players. Lately, Sanan IC invested also massively into the technology. So it will be interesting to see how they will grow. I mean, the main benefits of these Chinese players is that half of the electric vehicle market is in China today. So they have the advantage of having this local market with big end system OEM players really willing to build the local supply chain and to support them with the financing also from the government. So players, maybe to mention what we've seen lately, BYD, of course, starting building their own SiC production line from this year, invested more than $450 million in annual production capacity, reaching 240K units, for example. We've seen XPeng, so Chinese automotive players going public in Hong Kong, and also the deal they also have with possibly Infineon. We've seen NIO also demonstrating their first silicon carbide-based main inverter, and apparently working with onsemi. A lot of players invest in being present there. So historically, if we look at the partnerships, the investments, the acquisitions, so we've seen, as I said, so the secure of the supply with ROM acquiring SiCrystal. We've seen a lot of investments like Cree made this $1 billion investment in terms of capacity increase. They moved to 8-inch, building their new fab in Mohawk Valley in New York State. We've seen the acquisition. SK acquired this former DuPont business, again working on the crystal, trying to deliver good quality crystals. ST acquiring Norstel. II-VI also climbing in the value chain by also buying Ascatron, so ion implanter player. And very lately, we've seen Carvo investment in United SiC. So Carvo, a player which was not involved in this industry, acquiring United SiC. So we are seeing that a lot of players are looking in this industry and seeing the strategic move of being present there. So overall, if we look at the market share at device level, again, here we're looking quarter by quarter. This is the forecast we made the last quarter. So we published in September this year. So you would see ST Micro is making around half of the market at device level. So here we are counting in quarters, but we can also look at it annually. Wolfspeed then being present with ROM, Infineon also progressing. So in fact, we expect a strong revenue in 2021, 2022, especially owing to Tesla aggressive production plan. So last year they delivered like 500K vehicles with their Model S, Model 3, Model Y, all embedding the silicon carbide solutions together with some silicon technologies when they have the dual motor technology. But they build their gigafactories in Berlin, in Texas. So we're expecting maybe 900K vehicles being delivered in 2021, and that will drive ST being the main supplier of Tesla. And then we are seeing also Hyundai with their new 800-volt platform using silicon carbide-based solution from Infineon. So the progression will still continue. In the future, we are expecting other OEMs such as Audi, GM from their premium BEV models. GM announcing that they are building their own inverter internal capabilities. So OEM being very strongly intrusive in the supply chain, squeezing a little bit the tier one business model and directly discussing with the silicon carbides, the device or bare die providers. Okay, when we talk about silicon carbides, we hear a lot about cost. So for sure, we have to investigate what is the cost breakdown of a typical 1200 volt silicon carbide MOSFETs. And you would see here that most so half of the price is coming from the raw wafer, silicon carbide wafer. Then epitaxy would be a small cost. I mean, thin layer you need as it's the same material. And then you would have a lot of yield losses in terms of manufacturing. Here we are considering from the wafer up to device, first level package device. But then you would also have some losses if we would consider from the powder till the ball and the wafer. So there are a lot of losses at each level of supply chain. It's a very complex manufacturing to master. And indeed, the cost of the solution still is quite high. So what do we expect in the future? We are seeing today, the majority of the players are using 6-inch wafers. We've seen the transition to 4-inch to 6-inch, which has been not easy to deliver some good quality wafers. So the transition from 6-inch to 8-inch will really be a challenge, but should really help in delivering lower cost solutions, benefiting from the large wafer sizes. But at the same time, large wafer sizes, you really need to manage well the defects. So the defect density is the main parameters the player are looking at, and it directly will affect also the price. In terms of shortage, if we look at the overall investment, we don't see a shortage globally, but again, the demand will come from the few players being able to deliver high quality wafers. So the Cree, the SiC crystal, maybe in the future more the Norstel and so on, and other players, maybe Showa Denko and not Showa Denko, sorry, SK Siltron. So for those ones, it starts to be a bit tense if you look at 2024, 2025, where we expect the EV market to really boom. So overall, what we anticipate when it comes to the wafer size evolution is that, as I said today, the majority of the market is on 6-inch. 4-inch still is present, but will decrease. And we think 8-inch would start by 2024, 2025, if the players such as Cree are able to deliver good quality wafers, which at the moment is not the case. They are still have quite some defects problem. It really is tricky to come up with a good manufacturing process of a raw silicon carbide wafer, and then you need to do the device manufacturing. So Cree is pushing this approach. ST as well, they demonstrated their latest 8-inch wafer with Norstel during the last conference in Tours this year. Onsemi will also work on that with JTAT, and we've seen SiC crystal also have demonstrated the 200mm wafers. But as I said, we do not expect this to come until 2024, 2025. It's kind of mandatory for the silicon carbide industry to come up with these 8-inch solutions to really lower the costs and benefit from these higher size, higher diameter wafers, because the players today are also requiring large die sizes, which means you have to cope with your defect. The defect density needs to go lower, but the transition to 8-inch might not help in this respect. So it will really take time, a lot of fine-tuning, know-how, very good engineering team to deliver. So overall, if we look at the roadmap for silicon carbide-based devices, so as I said, first devices in 2000, it started with power supplies, PV for also where it got these miniaturization possibilities compared to a silicon-based, IGBT-based inverter. Now the boom is with electric vehicle when Tesla made the bets, very aggressive and risky bets of choosing silicon carbide in their model in 2018, and since then all electric vehicle players are evaluating the technology together with IGBT. Charging infrastructure also will boom, and silicon carbide is well positioned there. And rail, there are already some applications using silicon carbide in Japan for the Shinkansen or the high-speed train, in some of the tramway in Taiwan, in Europe. So it's also there, but lower volumes. It will be more appealing in the future with the, again, the energy consumption, the strong government regulation when it comes to CO2 emissions and green, more green energy. Okay, so I thank you for your attention. I hope I capture well this market, the different trends at device level from the players, also technology. We have more reports where we cover all these different markets for electric vehicle, the charging, the power module, the batteries, and now we are tracking the compound semiconductor industry on a quarterly basis, where we cover power silicon carbide, power GaN, RF gas and GaN, and the optoelectronics gas and indium phosphide, where we update our customers on a quarterly basis. So this is more or less how it looks like, and it will take some time maybe for the questions, and I thank you for attention, and I'm welcoming any question you may have. Thank you.
I have a question. Very nice question. Thank you.
I think Mitek, you are mute.
Oh, yeah.
Okay, so thank you very much, Claire, for this well-informed and comprehensive overview of power electronic market and scene. I am afraid that Claire has limited time, so we may be cut off in our discussion. So I am willing to collect all the questions and send them to Claire, if it's okay with you, Claire. And then you could answer whatever you can or want to answer, and then I could distribute your answers. But for now, let's use the time we have.
Yeah, I think we have 10 minutes. Yeah, if you have questions now, no problem. Let me know.
Yeah. So the question I had was, the silicon carbide, the market is highly dependent on the market penetration in the main inverter for automotive. So in the market analysis, how many cars do you estimate will use silicon carbide MOSFETs in the main inverter by year 2025 or so?
You mean how many players?
How many cars in the world do you estimate will use silicon carbide MOSFET in the main inverter by year 2025?
I'm not sure I capture your word curse, what it refers to.
Yes, how many millions of cars?
How many vehicles?
Okay.
Yeah, how many?
How many? All right. Well, that's the question that you asked. So what I can tell you today, indeed, when we look at these markets, the big ones are the Tesla, the BYD, the Hyundai. They're taking this solution. In the future, in the model, that's ongoing discussions we're having. It's all, so you know, GM also, well, all the big OEMs more or less announced that they are looking into that, the Volkswagen, the BMW, and so on. In the future, what could really maybe drive these markets is really the Chinese OEM. How will they adopt this solution for their 400-volt vehicle? Because for the 800-volt vehicle, I think there's a consensus that silicon carbide will be the preferred solution. Now, it all relies on the adoption of silicon carbide in the 400 vehicle range for OEM. What we're seeing is that they are really strongly looking into that, making bets, and it's a bit difficult to say who will take it or not. And when you discuss with the tier one, there's no real logic behind such a choice, because everybody is evaluating IGBT and SiC at the same time. But I think in the model, what we think is around 10% of the overall, I think, vehicle electric vehicle, BEV, I'm talking about the full battery electric vehicle, will use silicon carbide-based solution in 2026, while some players will tell you it's more 20%. And this difference will come from the adoption from the Chinese OEMs.
Okay, thank you.
Okay, so I've seen that there are some questions in the chat. It was from Moa Berkoros. Either you ask them directly or I can read them. What will be the ratio of cost of silicon carbide to IGBT year by year? Expected ratio.
So good point again. Indeed, we have a slide on that. I didn't include it. I think today, if I'm remembering correctly, silicon carbide is 2.5 more expensive than silicon when we do the full integration. Of course, the thing is that when you compare silicon carbide and silicon IGBT, silicon carbide is again a moving target, because silicon IGBT technology is progressing in terms of technology, and it's also being deployed on the 300 millimeter. We are seeing players investing in 300 millimeter platforms, so that will really help to lower the cost again. So that's a very difficult bet. So I don't have the numbers in my head, but that's something we can check if you want. I think it all comes from how silicon carbide will be successful in the 8-inch transition. If they can make this 8-inch transition, it will really help to lower the cost. But what about, they need also to do that with high quality substrates, high quality, lowering the defect density. So that's a really a strong step that the silicon carbide industry is taking. This is if we talk a device level, but in fact, the problem is more at integration level. If you would look at the inverter, and some banking companies have made comparison, like Tesla adoption of silicon carbide-based inverter compared to silicon IGBT, because they're also using some silicon IGBTs from Infineon for their inverter, for the dual motor technologies. Then the difference, the price difference, the premium you pay in the device is compensated by high power you can drive, some packaging possibilities you may have, and so on, because the junction temperature can go higher and so on. So overall, the cost premium at system level is not so important that at device level. And if you move to 800 volt vehicle, 1200 volt silicon carbide devices, then the price premium would be even less. And by my head, I think it was around 17% price difference today at system level between silicon and silicon carbide. But again, you gain in terms of efficiency, driving range, and so on. So a lot of BEV players are really willing to invest in silicon carbide to get this premium.
Okay, we have a question from Peter Benish. This is a little bit different about policies. It is, are there any policy missing, you think, that could enhance the transformation rate even further? Or
yeah, it's a very good point, because today, if you look at like the automotive industry, the regulation are on the CO2, the gram CO2 emission. So Europe having strong regulation, like 80 gram, I think CO2 gram per vehicle, and then the OEM will pay the penalty. We think in the future, as we are transitioning to more electric vehicle, this metric doesn't make sense anymore. So it will be more on the driving range per 100 kilometer. So more on the efficiency of the vehicle. So sorry, it will be let's say the driving range and the power level. I don't remember exactly the figure, but if you make such a plot, you will really compensate for the efficiency of your vehicle. And that's definitely, and we think that's the new metric that maybe they will use in Europe in 4 or 5 years from now. And this will again favor battery electric vehicle and silicon carbide implementation, because you would drive more, you will have a more efficient power conversion. And with such metric, you will directly see it.
Okay, there are more questions in the chat, but they are mostly from Moa Berkoros.
I would like, if I can comment, I'm Christian Fiere from Tusik Ascatron. There must be some mistake in your cost analysis for silicon carbide. The epi cost is almost same than the substrate cost, the production cost. Maybe 40-60 would be my analysis. So I think there is some mistake in the graph maybe.
Okay, so to be discussed with System Plus, because here they analyzed this the 100 volt MOSFET.
It's well, I know what it costs to produce the epi, and I know what you can buy the substrate for, and the price for a substrate, the price for an epi wafer is almost a double than the substrate alone.
Oh yeah, but here we're talking about the cost, not really the price, but the
no, but the cost. I know the cost. So I can tell you, it is not just 10% of the cost of substrate.
But again, so that's a discussion we could have with System Plus if you
want. Yeah, maybe there must be some mistake. And I thought I have to tell you, and then you can maybe discuss with them. You're welcome to come to also.
Okay, so maybe we could,
if you want.
Or offside discussion. Yeah, thanks for the feedback. Thanks.
So we maybe have time for one last question. Yeah, and then Moaber Koros from Volvo Cars. Maybe you could I can collect your questions and send them to Claire, because they are more time consuming. All your
This is thank you for a very nice presentation. This is Mohammed from Hitachi Energy.
Okay.
The cost comparison with silicon, you mentioned something 2.5.
Mm-hmm.
This number probably varies from which supplier to supplier, I think.
True.
That's one thing.
Yeah, true.
Secondly, this number is probably not valid for if you go to high voltage devices. Do you agree?
Yes, true. You're also completely right. Yes. No, true. I mean, you just need to have some kind of average, so metric. But I mean, have more details. You're right. It depends on the voltage level. It depends on the supplier. Again, yes, you're completely right. But I mean, we're talking to a lot of banking and financing institutions, so we need to simplify the message. And well, so of course, when you do that, you lose some of these important details. But I completely agree with you.
Yep. Thank you.
Okay, so we are, I think.
I have a question.
Oh, okay.
If it's possible. In your analysis to 2030, how do you see, or it's included, there is an emerging market now for huge electric jeep and ferries and electric buses and electric trucks. And these electric ferries, they have huge fast charging.
Yes.
And how is that going to affect the market on the silicon carbide?
Very good points. At the moment, we are only looking at 5 years outlook. So we stopped the forecast in 2026. We don't have a detailed model like we have till 2026, but we're looking at the trends for 2030. So I could not give you numbers because already sizing the market trend in the coming 5 years is really challenging. But you're completely right. In the future, there will be more of this electrification for other systems, like in boats or things like that. And definitely, we're talking about big systems and so on. But again, when we look at the market, usually the volume the BEV will take most of the share, because again, we're talking about 80 million units of thermal vehicle globally. But when you look at the share that the electric vehicle will have in 2026, 2030, it will definitely be the driving system. But the rest of the system will also make some nice market for silicon carbide. Yes, because again, efficiency. Efficiency will be key.
One other very short question.
I really have to leave. I'm really sorry.
Yes, okay.
Yeah.
No problem.
Okay, please, Mohammed, send me your question, and I will gather questions and send them to Claire. Claire, thank you very much.
Thank you very much, Claire.
Very nice presentation.
Thank you. I hope
yes,
we can see
thank
you.
Hope to see you again. I hope to see you at our conference in May.
Exactly. Yep. I hope. Okay. Stay safe.